he still didn't have a purple shirt.
That's true. Who needs to be smart when you have a purple shirt?
He didn't even teach physics.
Okay. So last week we talked about the concept of electric flux. In general, if I have three-dimensional space and I have a two-dimensional sheet within that space, and it could be imaginary, just could be a boundary that I just draw, and it doesn't need to be flat. Generally, it's not. So if I got like a curvy sheet in three-dimensional space and I got electric field lines going through it, we define electric flux. The electric flux through, and I notice I took the sheet and drew an infinitesimally small area, and we used the concept of the area vector, which we talked about last week, which will haunt you for the rest of your lives if you're doing physics and calculus. We said that the amount of flux, which is the capital phi, well, this is actually lowercase phi, but it's a phi. The amount of flux through that differential, the differential amount of flux through the differential area vector there, is defined as the dot product of the electric field and that area vector. If it's on the macro scale, if you do have a sheet that doesn't vary in its angle with the electric field, then it's just the flux, and then it gets the capital, which means it has lines, is just E dot A, right? And again, that's just the electric field strength times the area is length times width if it's a rectangle, times the cosine of the angle between them. If it's something like this, where the angle between the electric field and the area constantly changes, then we have to do an integral. And so to get the total flux here, I just have to integrate both sides. You integrate the left side, you get the total flux. Integrate the right side, and you get the integral over what we call an open surface. So you can write open surface at the bottom. Sometimes you'll see it as just a capital S. The integral over this entire open surface of all of the infinite number of infinitesimally small quantities given by E dot dA. Okay. And then again, if we make that substitution or a similar substitution, it's an integral over the open surface of E dA cosine theta. And the vector symbols go away because just like work and energy are scalars, right? There's no direction. The dot product of any two vectors gives you a scalar. So that tells you that electric flux is in fact a scalar. Okay, it doesn't. The electric field has a direction, but electric flux is just a measure of how many electric field lines are going through the surface. So it's just a number. Okay. Make sense?
It is a scalar?
It is a scalar, is what they call it, yes. So the thing is, we don't do integrals like this. We don't do open surface integrals. We don't do surface integrals except for the kind that we'll use Gauss's law to handle because it's pretty complicated. Note that when you graph a line on a two-dimensional set of axes, you have essentially what is a linear feature on a two-dimensional graph, right? Here, I have 3 dimensions. I've drawn the z direction. And I have a two-dimensional feature that I can then plot on that 3-dimensional set of axes. If I was actually going to plot this as a function, because you can take this sheet and you can find a function for it that will show you, you can take any curve, right, just about any curve, and find a function for it, right, in a linear, not linear, but you can graph a line on a set of two-dimensional axes using an equation. Well, you can graph a two-dimensional object, a sheet, if you will, on a 3-dimensional set of axes, but the equation then would be, all right, for every x and y coordinate, I'll get a given z coordinate, right? I can take an x and a y as the input, and I can get a z coordinate as the output. And you can do it the same way, y equals a function of x and y or something like that. But if, let's say that I take an x coordinate and a y coordinate, and then it will spit out a z coordinate, right? And so we would say in this case, z is a function of not just x, but of y as well. Okay. The reason that we don't do open surface integrals here is because if I want to integrate in all of the E dot dAs, I would be integrating with respect to x and y. And you probably have seen in certain places the jokes on math shirts where you have this weird thing where you got 2 integral signs right next to each other, right? And you'll see 3 integrals. You'll see triple integrals. And if I'm integrating with respect to x and y, then you'll see dx, dy. and it involves a little more work than we're going to learn how to do in this class, definitely, and even a little more than you're going to learn how to deal with in your calculus class here. When you get to third semester calculus in college, that's when you'll deal with double and triple integrals, and you'll be able to do problems like this. You'll be able to do line integrals and surface integrals, which we will do surface integrals in here, but they're going to be very symmetrical. And we're not going to use open surfaces. We're going to use closed surfaces, because it makes, if you remember what the videos talked about last week when it comes to flux through closed surfaces, it makes the situations that we're going to analyze a lot easier to deal with, actually doable, whereas we just don't know the mathematics how to do this at this point. Okay, so understand the concept of flux. It's just a measure of how many of these field lines, or the strength, the density of the electric field that's actually passing through a surface. That concept is crucial to understand, but we're not going to be integrating over open surfaces. We're going to be integrating over closed surfaces, which, as you'll see, makes it a lot easier to deal with. Yes, sir?
Did you hear about the tragedy of the cross-eyed physics student?
No.
He always tried to do double integrals instead of singular.
You know, on Friday, me and Mr. Little were talking about your dad jokes. And that was a good one. That was a good one. All right. Okay. That being said, let's move on. Remember that we defined, or if electric field lines point. Now here it's not quite so obvious, but when we have a closed surface, electric field lines point into the surface. We say that that is negative flux. If the lines point out of surface, we say that's positive flux. And the way that's just by convention, but it kind of makes sense if you make the analogy that Mr. Science Asylum was talking about on Friday. Think of like the field lines, which actually, if you have static charges that aren't moving, the electric field lines don't change, right? They don't flow. But you can think of them as like they do flow. And if they're coming out of a surface, it's like they're flowing away from a surface. Or flowing away from a point that you're surrounding with that surface, right? If I have a positive charge here, we know the electric field lines point radially away from that charge. And I can draw an imaginary surface, a three-dimensional sphere, right? An imaginary surface in which the field lines generated by that charge are flowing out, right? That tells you that you have a positive charge, right? Because a negative charge, field lines point in, it would be the exact opposite. Let's say I have that charge here, but then I just have a surface that's here. It's not enclosing that charge. Well, any field line that comes in will then go out, right? So the net flux there is going to be zero, because there's no way of drawing electric field lines if this is enclosing no charge. If the field line terminates, that means there must be a negative charge in there, right? In which case I would have negative electric flux going into that guy, okay? But if there's no charge within that shape, within that object, then the number of field lines that come in have to match the number of field lines that go out, so you get a net flux there of zero. Okay. Cool. And I like thinking of this is how because I don't know, you guys got some outdoorsy people in here? You guys outdoorsy people? Outdoorsy? Because if you ever go mountain climbing, this is on my way up Elbert. That's South Elbert here. That's not the tallest mountain in the Rockies. The tallest mountain in the Rockies is up here a low way. This is on my way up. But if you ever go up, right, you get to a point where you don't see rivers anymore. You don't see streams anymore because they haven't sprung out of the ground yet. You're up too high. And so that when you see a river at the base of a mountain, that river happens because springs, you have water just poking out of the ground. And then they end up converging into little streams, and then little streams converge into larger streams, and then those larger streams converge and become rivers as you go down the mountains.
Watersheds.
Water, yeah. Water cycle, right? The water evaporates, the sun actually does work to lift the water up. Then that water rains out on top of the mountain. A lot of that water soaks into the mountain. Whenever the water table on that mountain intersects the surface, then it springs out of the ground. And so it's not like water just springs into existence at that point, but if you were to put a circle around that point, you say, okay, that's a source of water flow, right? Think of charges as the same way. A source of electric field flow, but flow in quotes because it doesn't actually flow. But it's a good analogy. Cool beans? All right. So let's do an example just to kind of show.
Negatively or positively charged? Positively.
Yeah, we say positive. No. Hey.
So what we're going to do now is take a region with a constant electric field. So constant electric field strength. And the density of field lines would be the same everywhere. And this is the one instance in this class where we'll actually use this equation, integrate over an open surface, because the degree of symmetry here is going to make it a lot easier to deal with. Let's say I take a cylinder and I place that cylinder. Whether it's real or imaginary doesn't matter. Right? It could be an imaginary, as long as it doesn't affect the flow of electric field lines through it. We take this cylinder and we put it in the electric field so that its axis is parallel to the electric field lines. And we want to know the amount of flux passing through that cylinder. Okay. What's that?
Isn't it zero because it goes in and then out?
Yes. But we're going to prove it.
Oh.
Yeah. But that is true. Yeah, the flux is going to be zero. But let's use this formula, the formula for electric flux, to actually calculate it. To do that, I have essentially three different surfaces. This shape, this object, is created by the merger of three different surfaces. I have two end caps, and then I have one, what do they call it, the lateral surface area, the lateral part of the, is that the right word?
Wrap-aroundy thing.
The wraparoundy thing, that's the word. So I'm going to call this guy surface 1, the lateral wraparoundy thing is going to be surface 2, and then the other one's going to be surface 3. And we do expect the net flux to be zero, the same amount of electric field lines pointing in as out, but let's use this equation to actually show that. So I can say that the total flux here is going to be the flux, because I have three surfaces, through surface 1, plus the electric flux, I should say electric flux, plus the electric flux through surface 2, plus the electric flux through surface 3. What's that? Oh, let's hope not, because I'm hungry, and my lunch is after this class.
Intruder, wait, Mr. Graham is hungry.
Okay, so now so for surface 1, I have an integral. I have to integrate to get the electric flux through surface 1. It's going to be the electric field dotted with dA for surface 1. So I'll say this is open surface 1. And if I'm treating this surface by itself, it's a lone surface. It's not a three-dimensional object. So the flux through that guy, surface 1, is E dot dA, plus the integral over surface 2, which is also just E dot dA. These are vectors. The results will be scalars.
It would be like A of 1.
What's that?
It would be like dA of 1.
Well, not dA here, because, yes, I'm sorry, dA1, dA2, that's what you meant, right?
Yeah.
Yeah. The electric field we're assuming is constant over all surfaces in all space here. Just seeing if anyone was going to point that out. Good job, Mr. the Great. All right. Now, when we have to do an integral like this, and when we do Gauss's law, we're doing an integral like that every single time, I need to draw my dA vectors. Well, it is a three-dimensional shape that's made up of three surfaces that I've glued together. And you draw your dA vectors when you have a three-dimensional shape pointing away always. Just like a normal force is the force from the surface pointing away from the surface. So the dA here would be a small rectangle, circle, whatever shape you want, doesn't matter because we're taking the limit as its dimensions approach 0. That dA would point this way. So I'll call that dA1, of course, as Alex pointed out. The area vector for 2, notice the area vectors are all pointing radially away from the axis of the cylinder in any direction. I have trouble drawing in 3 dimensions, so I'm just going to draw that dA. And when I use Gauss's law for cylinders, I usually do the same thing. Just drawing it at the very top, so the dA vector points straight up. So that would be dA2. Now dA3 is on the other side. I can't see her, so I'm going to draw it in a little dotted line. Or a dotted box. So that's dA3.
Why did it go to the right, not the left?
This one?
Yeah.
Because it always points away from the shape. Always points away from the shape itself. So it's just, this is just the that end of the cylinder, right? This is dA1, this is dA2, and then the vector from that's going to be dA2. This is dA2, this is dA3, this is dA1. Okay. All right, so let's just do these integrals real quick. And you might say, well, these are going to be tough because it's like this weird surface integral, right? It's literally we're integrating over a two-dimensional object, two-dimensional surface that exists in a three-dimensional space for each one. But it's really not that hard because what happens when I add up all the dAs for surface 1? You get the area of a circle, pi r squared, right? Let's define the radius. I forgot to do that. Alex was supposed to do that, but he forgot.
Oh, man.
How dare you degree?
I left my radius at home.
So the radius of my cylinder,
Subpar.
I'm just integrating the electric field. And the electric field we said is constant. And so let's go the whole way. Surface 1, E dA cosine theta, plus the integral of E, this is dA1, sorry, E dA2 cosine theta. It should be cosine theta 1, cosine theta 2, plus the integral E dA3 cosine theta 3. This is over surface 1, over surface 2, over surface 3. Now, if these surfaces were curved, then it gets real complicated. You need third semester calculus concepts to deal with that. But if we have this symmetry, right? If we have the nice orientation of my cylinder and my electric field, it's pretty easy. Because the electric field is constant, right? So I can bring the electric field out of all three of these integrals. The cosine of the angle is going to be constant, right? The angle itself will be constant because the surface is not changing its orientation. So it's going to be E cosine theta 1 times the integral over surface 1 of dA1 plus E cosine theta 2 times the integral over surface 2 of dA2 plus the integral over surface 3. Wait. E, the electric field, times the cosine of angle 3 times the integral over surface 3 of all the dA3s. What is the angle between dA1 and the electric field?
Would it technically be
180.
180. So what's the cosine of 180?
0.
What's the cosine? Who said 0? Okay. -1, right? So, and what happens whenever I integrate all the dAs there, dA1? I get the area, right? And so I can write that as A. I can write it as pi r squared, whatever you want. I'm going to go ahead and just write it as A, though, just to make my life a little easier right now. So it's just going to be E times A1 times -1. Right? Because the cosine of the angle is -1. Look, I just did a surface integral. I just integrated over a two-dimensional surface that resides in three-dimensional space. It was that easy.
Wow.
When we use Gauss's law, generally the integral is the easy part. Dealing with the charge density or the charge that's involved in the problem is the more difficult part. So we're going to see that in those crazy equations where you got the integral symbol and you got the little circle in there, it looks complicated, but it's really not that bad. It's really not that bad. It's like this. You integrate over the whole area, you get the total area of a shape that you know of the area of. Okay. Now, here it's going to be E times the area dA2. Well, if I knew the length, if I knew the length of the cylinder, then wouldn't the area of dA2, or the lateral area, the wraparoundy part of the cylinder, wouldn't its area be 2 pi r times L, right? If you take a cylinder and you unwrap it, right, the circumference is 2 pi r. If I roll it out, that circumference is now this dimension, and then you multiply it times the length of the cylinder, and you get the area. What if we don't need to do that and we can just write area 2? Is that what you're going to say?
Or we could just write area 2, or we could just write 0.
Yes. So E times area 2 times the cosine of, oh wait, yeah. What's the angle between dA and the electric field, Trent?
90.
90 degrees. What's the cosine of 90?
0.
0. Okay. And then plus, I integrate over all dA3s, and I just get the total area for that circle. It'll be E times A3 times the cosine, right? Times the cosine of what's the angle between dA3 and the electric field?
0.
0. The angle is 0, so the cosine of the angle is 1. So it's EA3 times 1. Now, if this is a cylinder, aren't surface 1 and surface 3 the same area?
Yes.
Yeah. So I can draw out the A1 and the A3. And the only one I need to differentiate is A2.
But if it's multiplied by 0.
Yeah. So I have negative EA. This guy's 0. Plus EA gives me a net flux of 0. Which Logan did in his head before we even started. Right.
All this math.
Now, the reason I pointed that out is to show you that when we see integrals, especially when we start applying Gauss's law, we will do so to make our lives easier. How do we do that? By recognizing symmetry and drawing our surfaces so that there is symmetry, so that the total flux through a surface is either 0 or it's some amount that you can easily determine just by looking at the area of the shape you're dealing with. Okay. So you're not going to see many problems like this, but you're going to be doing integrals like this all the time, right? And you're going to say, well, the integral over that area is literally just the area. That's all you got to do. When you get to third semester calculus and you start dealing with the flux through surfaces like this, then yeah, it's going to be more complicated, but not in physics C. In physics C, the integrals, for now, the integrals that we encounter shouldn't be the most difficult part of the problems that you're going to solve or the situations that you're going to have to analyze. Okay? Sound good?
So really, the second piece doesn't even have to be there at all because there's no lines pointing through.
Yeah. And that's a good thing to note as well. If you have electric field lines that are traveling this way and they're perpendicular to the area vectors or just parallel with the surface itself, there's no flux through the surface. Yeah. All right. That being said, well, before we move on, I'm going to erase everything. Okay.
After I copy it down.
Okay. Well, you better hurry because I'm almost done erasing it.
I got it.
Good.
Photograph it.
All right.
Wait a second, did you rewrite all of it?
Wait, did we? So we're supposed to be taking this.
You're silly. Okay. Let's take. Now we're gonna start using Gauss's law.
We're gonna start doing what we were planning to do the entire time.
Yes. Let's say we have a positive point charge. I will call him Q. And let's say I want to know the electric field at this point P. I know based on this charge and my knowledge of how charges create fields, I have an electric field that points this way, right? At point P. So what we can do in order to easily determine the strengths of electric fields are use what we call Gaussian surfaces. So what you do is you enclose the charge. It doesn't have to be a point charge. This is just where we start. It could be a long line, a linear distribution of charge. Could be an area distribution of charge. Could be a volumetric distribution of charge. But here we start with just a point charge, something that we can consider to be a point charge, and we enclose it in a Gaussian surface. And we do so that that Gaussian surface, like what we just saw with the cylinder, when we do an integral over that surface, the two-dimensional surface in the three-dimensional space, we do so that it's really easy to, how do I word this? So that the electric field is constant over the surface or is zero over the surface. Okay, let me show you what I mean. I'm going to take this chart. How can I draw? What shape could I draw around this object in three-dimensional space, around that charge, so that the electric field on that surface is going to be constant over the entire thing? A sphere, right? That's the only way to do it. So I can draw a sphere. Now notice that this sphere does not exist in real life, but neither do vectors and neither do a lot of other things we deal with, but they are very useful tools. This is three-dimensional, right? It's a three-dimensional sphere that's going to have the same electric field all over it. And so I can kind of draw that by doing this. Here's my three-dimensional Gaussian sphere. In this case, it is a sphere, but in general, this is called a Gaussian surface. In this case, it's a sphere. It's not always going to be. Sometimes we use cylinders. And I'm also going to draw my area vector. And I'm going to draw it where I see the electric field vector that I'm interested in, right? We know that we have that same strength electric field everywhere on the surface. If it's not the same everywhere on the surface that you've chose, then you've chosen poorly. Okay. If it's not going to be the same on everything, then the integral's much, much more difficult to do. That's why you draw it such that you have the same electric field everywhere on the surface. And then we draw our area vector. So here's a little area vector. So dA. Okay. Now I'm going to define something. We know what charge is. But what we want to talk about when we're using Gaussian surfaces is the charge that is enclosed by that surface. And so usually that's written as Q, E, and C for enclosed. Okay. And if I look at the charge that's enclosed here, and I try to relate it to the electric flux that's going through my chosen surface, please understand that it doesn't matter how big I make that surface. I get the same flux either way, right? I have a certain amount of electric field being generated by this positive charge. No matter how big I draw this surface, you'll have the same amount of electric flux. It doesn't matter. This is why we use the integral, for one reason why we do the integral version of Maxwell's equations first, by the way, because if you're talking about the differential version, then you are talking about as the volume gets infinitesimally small, the limit as the volume of your surface approaches zero. And then you have the multivariable calculus part, and you got the divergence. Gauss's law is written in terms of the divergence, which again is that weird upside down triangle operator that you don't need to worry about in this class, but will be in your future. Okay. But so that was a small aside, sorry. So it turns out that when I enclose this charge by a Gaussian surface, no matter how big, and really no matter what shape, it could be any shape, you're still going to have the same electric field lines leaving it because it has the same charge enclosed. Turns out that the relationship between this enclosed charge and the amount of flux is directly proportional. So I could say that the enclosed charge is directly proportional to the amount of electric flux that is emanating from the surface. And it turns out that you can experimentally determine that the proportionality constant is our old friend permittivity of free space epsilon naught. So that being said, I can turn this proportionality into an equation. Simple linear proportion. The enclosed charge, and by that I mean the charge enclosed by the Gaussian surface, is going to be equal to epsilon naught, permittivity of free space, times the amount of electric flux that is passing through the surface that I've enclosed that charge with. And then I can just divide both sides by epsilon naught, solve this for the electric flux, and that's going to be Q enclosed divided by epsilon naught.
So it's the charge enclosed in the free space around it? Is that kind of what it's supposed to be? Because
It's the charge that's enclosed by the Gaussian surface that you've surrounded it with. Yeah. Does that make sense?
Yeah.
And this could be any shape. It could be a cube. It could be something weird, some blobby looking thing. What?
A dodecahedron.
It could be a dodecahedron. But trying to determine this mathematically with a dodecahedron or some random shape, it's difficult and requires calculus that you're not going to learn until you get to college.
well, we could
And
just-
that I might have forgotten at this
What
point.
about like a pyramid?
A pyramid, it still would be difficult. The reason being, and this is something you want to know, is because you use any other shape but a sphere, the electric field is going to be different at different points on that shape. We want this symmetry. It'll make the integral that we'll have to do much, much, much easier, as you'll see right now. So we have an expression for the electric flux. It's the integral of all the infinitesimally small dot products of E and dA, right? Only, like we saw before, where we were dealing with these open surfaces, meaning just a two-dimensional surface that was placed in a space, a three-dimensional space that had electric field lines going through it. Now we're talking about a closed surface. And that's where that thing comes in. That little circle that's placed on the integral symbol. All that means... Now, as you'll see, it could either mean a closed surface or it could mean a closed loop. When we get to magnetism, when we start talking about Ampere's law, a similar integral will not involve a closed surface. It'll incorporate a closed loop. But for right now, that little circle there stands for closed surface. And that is just our definition for electric flux. So that equals the enclosed charge divided by epsilon naught. This is our version, the integral version for AP Physics C of Gauss's law. In parentheses for electric fields. But as I said last week, Gauss's law for magnetism is real simple because it's just always zero. The integral of the magnetic field dotted with dA is always zero because there's no shape, there's no three-dimensional closed shape that you can draw in any space where you have magnetic flux not being zero. Okay.
I understand all that more. Because the point P is on the...
Point charges can either create or absorb electric flux. The tiniest bar magnet, which is an electron, has the magnetic fields coming out of one pole and going into the other pole. You can't have a magnet that has just north pole where magnetic flux is pointing away from just a north pole. It always will come back. Even within a magnet itself, if you have a magnet, magnetic field lines will loop around always, no matter how small it is. Excuse me. Okay.
So if we were trying to calculate the electric charge at point P, we isolate the electric field.
Yeah, we're gonna do it. We're actually gonna use Gauss's law to determine an expression for that electric field.
Oh, okay.
And so our steps, in general, are steps for using Gauss's law.
Let's see if we can come up with another good acronym.
You draw your Gaussian surface, and you do so. There's some bullet points here. Draw your Gaussian surface so that the electric field is constant over the entire surface. Now, sometimes you want it constant over one part of the Gaussian surface and then just zero on the other part. When we use Gaussian cylinders, you'll see that ends up happening. So you either want it to be just constant or zero. So maybe for 0.
0 is constant.
Yeah. But you can have a Gaussian surface where you'll have a part of it where it won't be 0, and then another part where it is 0, and we can still use Gauss's law to handle those situations. And we also want to look for symmetry, as you'll see when we move on and do more examples. You'll see what I mean. Look for symmetry. And then I have it written here. Otherwise, this is how I've written it on my notes. Otherwise, the integrals are ... difficult. Meaning, I probably would need to do some research again because I haven't done them in so long before I could actually do them. Beyond the scope of this class, for sure. And that's actually a true statement. Okay. But as you'll see, unless you're dealing with really complicated electronics, what we're going to learn in this class is pretty much good enough for government work. Better, in fact, because it doesn't require that much to do government work. Okay. So let's use Gauss's law to figure out the electric field here at point P.
Wait a minute, this is government work. It's a public school.
Yeah. That's what I said. Okay, so let's go ahead and use Gauss's law. So I'm going to write it first. The integral over the closed surface, which is why I draw that. And I know it's a closed surface and not a closed loop because I see a dA in there. That means I'm adding up the area, right? An area that bounds, that surrounds the space in which the charge lies. So the integral over the closed surface of E dot dA is going to equal the enclosed charge divided by epsilon naught. Again, this looks scary for some, but then we realize I've drawn my Gaussian surface so that the electric field is constant over the entire surface. If that's true, the electric field can just come out, right? Before I do that, let's do this. The integral over the closed surface of E dA cosine theta equals enclosed charge over epsilon naught. What's the cosine of theta for all E dAs? E dot dAs. What's the cosine of the angle?
1,
Oh,
2.
yeah, of 0 degrees. So it should
0 degrees. Oh, okay, sorry. Yeah. No matter what dA you draw, if I draw my dA here, it points this way. So does the electric field. If I draw my dA right here, so it's like pointing towards you guys, the dA is, well, so does the electric field. I've drawn my Gaussian surface so that there's symmetry when it comes to the electric fields and the area vectors, and so that the electric field is constant over the whole thing. So because I've drawn my Gaussian surface, and according to those specifications, the cosine of the angle is just 1, and the electric field is constant. Meaning I can bring out the area, the electric field. The electric field times the integral over that closed surface of all the dAs.
Is it no longer a vector?
What's that?
Is it no longer a vector?
No. Dot products give you scalars.
Okay.
Yeah. Just like work. Remember, work was F dot dr, and work itself is a scalar. Same thing here. When you go from here to here, the vector symbols just go away.
No more.
Now we will do cross products later. Cross products spit out vectors. Yeah. The three vector operators that you learn in multivariable calculus: the gradient, the divergence, and the curl. Divergence is a dot product, so that's going to be a scalar. The curl is a cross product, so that's going to be a vector. The gradient is a vector. If you have like a hill, the gradient, like a hill is essentially a two-dimensional surface in three-dimensional space. The gradient just points in the steepest direction. Right? It's the derivative. It's the derivative with respect to both directions that you're integrating, that you're differentiating over. Again, that's beyond the scope of this class, but those are things that I wish I at least had in my mind when I was learning about them, because it was really hard to learn about this stuff when it was my first exposure ever to it. Anyway, so I have the electric field times the integral of all the dAs, meaning add up all the dAs, and that just equals the enclosed charge. What's the enclosed charge here?
Q.
Q. It's just Q over epsilon naught. When might it not be Q? When I have a Gaussian surface drawn inside an insulator that has a constant charge distribution inside of it, right? So if this guy had a uniform charge throughout its whole volume, and I want to know the electric field inside of it, then I would use a Gaussian sphere that is inside of it, in which case the total charge would not be enclosed, right? We'll talk about that tomorrow. Not tomorrow. What happens when I add up all the dAs?
A.
What is A, though?
Surface area.
Surface area of a sphere, which is what?
4/3 pi r cubed.
That's volume of a sphere.
Oh, surface area.
I don't know. Google knows.
Something. One of them.
Something
You know what
with
else
pi
knows?
in it. Something with pi. in it.
Your formula sheet.
Oh, I was gonna say you were correct.
Is it 2/3 pi r squared?
Isn't it just 4?
Uh,
Okay, now you got me second guessing it.
4 pi r.
4 pi r squared. Yeah, it's just 4 pi r squared.
Something.
Yeah, sphere. It's on your formula sheet. It's 4 pi r squared.
I was looking at circle and I was very confused. I was like, what?
So I like writing it like that for reasons you'll see. And that's going to be Q over epsilon naught.
wait, is the antiderivative of 4 pi r squared 4/3 pi r cubed?
The integral of 4 pi r squared is 4/3 pi r cubed.
Yeah, that's what
Oh, yeah.
So,
And so it's like you integrate all the stuff inside of the fluid, put it together.
so the integral of the surface area
Is
is the volume.
Yeah, I think it's a little more. I think, yeah.
because wow.
Because
The
of
radius approaches 0.
Now it's 4 pi r squared because that's going to be the shell, and then times dr, right? Dr is going to be the thickness of the shell, and so when you add up the volume of a infinitesimally thin spherical shell is 4 pi r squared times dr, and then when you integrate all that, you get the total volume of the sphere, which is 4/3 pi r cubed.
Wow.
Good observation, guys. Oh, that makes me happy.
you passed for today.
Yes. Just you two. Alex too. Everyone else. Now remember, we want to know the electric field at point P. So the electric field I just divide by 4 pi r squared. And I get 1 over 4 pi epsilon naught times Q over R squared.
This looks
Wait a
really
second. Oh boy.
Where the electric field is KQ over R squared.
Wait a
Wow.
second.
Okay.
This turned out to be really simple.
Hence where the 1 over 4 pi epsilon naught comes from, right?
Wow.
You could say.
Wow.
Now, you can get started. There is a current quest assignment. You can get started on it. Just don't go beyond the first few questions. Because one of the first questions, whenever you see the first question say, what's the electric field at a point within the charged insulating sphere, we're going to talk about that. Not tomorrow, but here's the deal, guys. Here's the deal. I'm not going to see you tomorrow, right? You got a senior meeting. I'm going to be watching a bunch of freshmen and sophomores while the juniors are taking their PSAT. So
Good luck with that.
I'm going to make a video tomorrow morning where I'll work over some of the examples. I'm going to talk about what's next on the agenda. 'Cause I was looking at the schedule. I don't want to take a day off just because of PSAT. So I'm going to make a video where I talk about how to use a Gaussian sphere, to determine the electric field strength within a charged insulating sphere, how to use Gauss's law to determine the electric field inside a charged conducting sphere, which will have an interesting result, how to determine the electric field due to an infinitely long wire. We've already done that, but remember I took up 2 pages. So Gauss's law, using Gauss's law to do that is a lot easier, as you'll see. And then the electric field due to a conducting sheet. So I'm going to make a video tomorrow morning that you probably want to watch before you come back on Wednesday. Okay.
All right.
Especially since either Wednesday, Thursday, or Friday, I'm not going to be here depending on some lab work my wife is having done today. She's going to have a procedure done either Wednesday, Thursday, or Friday. We don't know which day yet, but one of those days I'm going to be out. And Joe will be teaching class that day. Okay. So just keep an eye on Canvas tomorrow. It's been fun. Let's do this again sometime.